Good evening, everyone. Welcome to the NPTEL problem solving session for the course Robotics Basics and Selected Advanced Concepts. This is the problem solving session for week 8, in which uh, dynamics, mostly dynamics of serial and parallel manipulators, have been discussed. So I'll just go through the assignment that is given for this week, and we'll discuss some of the notes as well. So, yeah, this week. Okay, mostly it was about dynamics of serial and parallel robots, or more specifically manipulators. Okay, for dynamics, okay, like two approaches were introduced, two methodologies. One is using Lagrange's equation, okay, and the other is the recursive Newton-Euler algorithm. Like this is specifically for serial robots. Okay, this is abbreviated as RNE. So just a quick overview of what was Lagrange's equation of motion. So in Lagrange's method, what is done is a quantity is defined called the action potential. That is the okay. So definition of this quantity is the difference between the kinetic energy and the potential energy of the system, okay, of the complete system. Okay, and it is assumed that all of them, or this particular quantity, okay, it is written using a set of generalized coordinates. Okay, so this q is a vector. Okay, and so what are the Lagrange's equation? They are the time derivative of partial derivative of L with q dot. So if we write it in the component form for every component of q, okay, it comes out like this: del L over del qk. And let us not take constraints. Okay, so without any external forcing or any constraints, okay, the form of Lagrange's equation was this. Once external forces are added, I hope I'm recording the right. Okay, so this changes to okay, but before this, we will write the same equation without any external forces in vector form. So to write this in vector form, by del q is equal to the zero vector. Okay, now if there is an external force, okay, if, if there is an external force acting on, like acting or represented in another space, okay, such that the work done by the force is given by F dot x, okay, and we can say that x can be written as a function of q. X can be written as a function of q. So to write F or to include F in the equation of motion as an external force in the Lagrange's equation, we need to convert F, like forces in the X space to some generalized forces in the Q space. Okay. And how it is done is it is done using a coordinate change where we say that the work done due to this force should be equal to the equivalent work done due to the generalized force. Okay, and from here we can say that this q is f dot dx, or more specifically it should be del, okay, partial x over partial q, and in matrix form it becomes del x over del q transpose f, and this quantity is termed as the Jacobian, right? The Jacobian between x and q, between the two spaces. So the modified Lagrange's equation, they look like this. Del q. Now if f are already specified in the q coordinates or in the q space, then this matrix, okay, this del x over del q, okay, it will become del q over del q, and it will just become an identity matrix. Okay, if f are, or if the external forces or torques or whatever it is, they are already specified in the q space. Okay, this is your q. Okay, now, and also if there are any constraints, okay, so constraints are also included in this in a similar way. Del q dot del over del q, like you can write this as, force you want to write as force applied on the body, then is equal to, let us call this J transpose. Okay, this del x over del q. And what is phi? Okay, so phi is the Jacobian matrix of your holonomic constraint or whatever constraint you have. Okay, so I should not write it as capital phi. Okay, so this we write there as in this form. Okay, you differentiate it once, and this phi is what goes here. So in the presence of external forces and constraints, this is how Lagrange's equations get modified. So this is all there is to writing the equation of motion or the dynamic equation of motion for any system that has holonomic constraints or that has conservative, non-conservative external forces. And friction is also included in the same set of equations with a slight variation that is given in the lectures. So I'll just quickly go through the questions that are there in the assignment, both of them, and I will just give some hints regarding those. So hmm, so uh, yeah, let us continue with the assignment. So well, most of these questions they are directly from the lectures notes, and if you go through the lecture online lectures like live or the lecture notes, you will be able to answer them. So the first question is about the inertia matrix. So there are just some properties that the inertia matrix has and some that it never has. Like it is always positive definite. And you can also do some, yeah, wait. Where is- hmm. One can also do some preliminary, you know, just checks, theoretical checks to make sure that even if in any imagine if in any space or in any vector space the any choice of coordinates, if the mass matrix does not appear to be symmetric in the kinetic energy term, it has to be symmetric because only the symmetric part of any matrix contributes to the kinetic energy. Because if you take any general matrix, let's say M, and you try to do X transpose AX or X transpose MX, then the antisymmetric part of M, if you decompose M as the sum of the symmetric and the antisymmetric parts, then the antisymmetric part will go to zero, and what you will be left with is just X transpose and the symmetric part of M times X. So like the mass matrix will always be, positive, definite, and symmetric. And then the next question is about the Lagrangian formulations. What do you require? So yeah, like if you have gone through the lecture notes, you know that the difference between kinetic and potential is required for the complete system. Okay. And then Lagrangian formulation for, okay, like now this is about the friction and about the applicability on what kind of robots it is applicable. So for friction, there is some notes that are like there are some points that need to be kept in mind, and they're given in the notes. And the Lagrangian formulation for parallel robots, again, it is directly from the notes. And then there is definition of general forward dynamics and inverse dynamics also, and the Lagrange multipliers. Yeah, so the Lagrange multipliers, they like as we saw in the sheet earlier, they appear as external forces, right, in the constraint space. And then there is a question about non-holonomic constraints. How are they included? And this is also given in your lecture notes. And then, yeah, the question on inverse dynamics. Uh, and the last question is about the recursive Euler algorithm and the computational complexity. So this recursive Newton-Euler algorithm is only used for the inverse dynamics of serial robots. Okay, so this is a standard algorithm that is used in robotics for simple serial robots without any friction or anything, and only to calculate the inverse dynamics, right? And it has a linear complexity. Okay, and the state space. Okay, so the state space includes if your, you know, generalized coordinates or whatever your choice of coordinates you have, if so the size of your state space depends on the choice of coordinates. So if you have n coordinates, then the state spaces consist, the state space consists of those n coordinates and their rate of changes of each of those coordinates. So essentially, if you have n coordinates, then you will have n plus n. Okay, so n coordinates and n rate of changes of those coordinates. So basically 2n number of variables, and there will be 2n uh, first order differential equations. When you convert any equation into state space form, for any dynamic system, it will convert to 2n first order ordinary equations. So this is, I think, it for the this multiple choice assignment. And then for the subjective assignment, you have been given a very simple 2 degree of freedom planar PR robot, and you've been asked to derive the equation of motion for this robot. So what you're supposed to do is you're supposed to write the velocities for both of these objects that comprise that make up the system, the mass m1 and this rod of mass m2. Write the total kinetic energy, write the total potential energy, take the difference, and use the Lagrange's equation to get the equation of motion. Okay, and then uh, yeah, okay, and then in the following question, okay, you have been asked the inverse dynamics essentially, right? That for a straight line trajectory, plot the force and torque required. Okay, so the force and torque required come from the inverse dynamics. So this can be done again similar to what has been given in the lectures, right? From the equation of motion, you invert them to get the expressions for torque and the forces, and from there in those equations, and for those equations you have been given already what is the trajectory for d for one of the displacements, and what, like, it's for a constant theta, right? So from these trajectories you can get d dot, d double dot, and theta dot, theta double dot. You put them in your expressions for tau in the right hand side, and then you will just get expressions for the forces and torques, whatever whatever is required. And you just have to plot, you have to do this in MATLAB. So yeah, hello Pranav. Yeah, hello Pranav. Can you hear me? Yeah, yeah, sure. Like, without raising your hand, you can ask. Yes. So I think I'll just discuss with you also what I was sharing earlier. Yeah. Yes, it is a session. Okay, and I was just discussing, I was basically recording what is to be done in this assignment, and I was going to upload it. But if you have any doubts, you can ask right now. So I'll just go through what has to be done in the subjective part again. So in the first question, you have been given a basic 2-hour planar robot, and you have been asked to derive the equation of motion for this robot. So this is a basic 2 degree of freedom planar robot, and you can derive the equation of motion using the Newton-Euler equations, but it would be much easier to just use the Lagrange's equation. So you write the kinetic energy for this mass m1 and this rod of mass m2. So there will only be a translational kinetic energy for mass m1, but translational plus flotational kinetic energy for the rod. So you write the kinetic energy, you write the potential energy of this system that will be due to this rod. You take the difference, and then you use Lagrange's equation to get the equation of motion. Okay, I think that will be sufficient for the first uh, question here. And then in the second question, you have been asked the required force and torque to track the trajectory that is given here. Okay, so to get the required forces and torques, what we require is the inverse dynamics of any system. And inverse dynamics we get from the equation of motion. So basically, in equation of motion, we rearrange that to get the expressions for the external, whatever external torques and forces are required, basically. And using the trajectory that are given, you get your, basically, d is given as a function of time. So you can get d dot, d double dot, and theta is given as a constant. So theta dot and theta double dot are zero in this case, but essentially you have all the degrees of freedoms and their rates. Okay, so you just put them in the right hand side for inverse dynamics, whatever equations you get from the first question after rearranging the solution of first question, and you'll have your expression for forces and torques. Okay, and then you just have to plot them. And then in the third question for the same robot, okay, plot you have to plot d1 and theta as a function of time. Okay, but what is given is gravity acts downwards and the external forces and torques are zero. So there are no external forces and torque. Okay. And the initial conditions, basically from where your system starts at t equal to 0, is this. It starts at 0.5 meter displacement and 30 degree, okay, 30 degree angular displacement for the rod. Okay. And then you have to just integrate the system forward in time, keeping external forces and torques as 0. Okay. So from the questions which will be graded, it is only a single system that you have to deal with. And In the additional question that has been given, you can just try to, you know, go through the Lagrange's method or just Lagrange's equation for any general system, and then try to get the expression that matches. You know, you will get an expression for the mass matrix M, and then you can write the coefficient of the mass matrix, or not the coefficient, the elements of the mass matrix in a particular way. That will reflect in the expression for your Cij. Okay, so this is how you can write this relationship. Yeah, so I think this concludes both the parts of the assignment that you guys have to do. So I will conclude here unless you have any other doubts. Pranav. Yeah, okay. Then you can leave. I'll just close the meeting.